So class, today I'll be talking about yo-yo physics. The yo-yo is a object typically made of wood in this case. It's got two halves connected by a smaller radius dowel, and around that is wrapped a string. For the purposes of analysis, I'm going to assume that the string has no thickness, so as the yo-yo unwinds, the radius of the inner portion will be taken to be constant. Otherwise, the analysis gets rather complicated if you don't assume that. And by yo-yo physics, I really mean I want to find the acceleration of the yo-yo as it unwinds and the tension in the thread as it unwinds. I'm not trying to analyze any of the fancy tricks that one can do with these yo-yos. So let's look at the most basic type of physics. Let's take this yo-yo to be a circular object. The outer radius of the yo-yo does not concern me. I just want the inner radius because that's the radius around which the thread is wound. And let's take this thread to be, like I said, infinitesimally thin. The person is holding it, but that doesn't concern me either, so I'll just attach it to a ceiling. And we're going to let this unwind due to its own weight. So here's the force of tension and the force of gravity, which I'll draw bigger than the force of tension because it is having an acceleration in the downward direction, which I'll indicate like that. And it's also accelerating in the angular direction. So if you look at the sign convention, alpha is going to be into the page and A is going to be down. Now there is a connection between A and alpha. Let's write that down. It's the so-called no-slip condition. And the no-slip condition is A equals R alpha. So if you write the sum of all the torques that act about the center of gravity of the yo-yo, which is this point here, that's going to be equal to I times alpha according to Newton's second law of rotation. Now the sum of all the torques acting through the center of mass, gravity cannot be one of those because gravity acts through the center of mass. So the distance between gravity and the center of mass is zero. It produces no torque about the center of mass. The force of tension does produce a torque, and that's given by the radius, this little r, times the force of tension times sine of the angle between the two, which is sine 90 in this case. So it's rft sine 90 degrees equals IC. And here I'm going to use the no-slip condition, A upon R. And this can be solved for the force of tension. I'll take the R over to the other side, so I get ICA over R squared. I'll call that equation 1. The other thing the yo-yo is also doing is it's translating in the downward direction, which I'll take to be the positive y-axis. So we have to write Newton's second law for that direction as well. Let's do that here. The sum of all the forces in the y direction equals mass times acceleration in the y direction, is what Newton said. So that's mg minus ft is equal to ma. Let's call that equation 2. And equation 1 and equation 2 can be solved together. Let's do that next. I'll substitute for ft here. So I get mg minus I sub c a over r squared is equal to ma. Now I can take the a over to the other side. So I get mg equals ma times 1 plus IC over mr squared. Let me explain what I did here. I took ma outside, and to compensate for that, I put an m in the denominator of this term. That's all I did. So I can cancel out the m on both sides, and this gives me the acceleration of the system. Dividing both sides by this factor, I get it's g1 plus I sub c over mr squared. Well, that's a great result to have because it looks right. For example, this proves the acceleration is less than g. That had better be true, because if the acceleration were equal to g, the yo-yo would be falling freely. In other words, you've let it go. So here it unwinds, so it's not going to be that fast. So the next thing we can do is to find the tension by substituting it back into the expression for tension. So I get F sub t is equal to I sub c over r squared times A, which is g divided by 1 plus I sub c over mr squared. I'll do the same trick here as I did there. So I'll write this as I sub c over mr squared divided by 1 plus I sub c over mr squared times mg. The reason I wrote it like this is to show you that it's less than mg, because this quantity is certainly less than 1. So this proves that ft is less than mg. That also makes sense, because if you were holding the yo-yo, you would not need to hold its full weight as it's getting away from you. You'll only hold a lesser weight than the full weight. Now a good exercise is to try to get this result using energy. So let's try that next. So for the energy method, we have to let the yo-yo unwind by some height and try to find what happens. So let's draw a new diagram here. Well, this time the yo-yo is going to unwind with a angular velocity omega, and the center of mass of the yo-yo is going to move down with some speed, which I'll call v here. And the yo-yo is going to be descending some height, so I'll call that height h. The no-slip condition connects v and omega. Remember, this is still that distance little r. So the no-slip condition this time is v equals r omega. We've got to use that in our equation. So let us write the energy equation. The potential energy lost by the yo-yos descending must be converted into both translational and rotational kinetic energy. So that's the energy accounting. Let's write down the expressions. The potential energy lost is mgh, and the translational kinetic energy is 1/2 mv squared. The rotational kinetic energy is 1/2 I omega squared. And here I'm going to use a no-slip condition to get rid of omega squared. So let me write the next step. mgh equals 1/2 mv squared plus 1/2 I sub c v squared over r squared. And then I have to pull off a similar maneuver like here. Take the m outside, so I'll do that. 1/2 mv squared times 1 plus I sub c over mr squared. you observe it's our favorite factor that keeps showing up everywhere. It's showing up here as well. So cancel out the m's, and our final step is to solve for v squared, which I'll do here. So that tells me v squared equals 2gh, because I transfer the 2 over there, divided by 1 plus I sub c over mr squared. That gives us the velocity squared, though. We still need the acceleration. Now you can go ahead and find the acceleration using 1D kinematics, because the y direction is one-dimensional. But I'll teach you a more general method which applies to any problem where you don't necessarily have constant acceleration kinematics like you do here. And that method is to differentiate both sides. Calculus allows you to do anything you want, and you can differentiate both sides. So the left-hand side by the chain rule is going to give me 2v dv by dt. And the right-hand side is 2g times dh by dt. The denominator factor, it does not depend on time, so it just escapes the differentiation. 2 cancels out. Now the rate of change of height is precisely the translational velocity, so that cancels out too. And so I am left with the acceleration equals g divided by 1 plus I sub c over mr squared. Which is precisely the result we got earlier from Newton's second law. What about the force of tension? Can we get the force of tension using the energy method? Unfortunately, the answer is no to that. And the reason for that can be seen as follows. The force of tension actually causes no displacement. The point of contact between the thread and the inner portion never moves. Now, to fully understand why, I would recommend going back and watching the rolling without slipping video I had last week. In that video, I showed that when you have a wheel that's rotating, the point of contact of that wheel with the ground never changes. So you can think of the yo-yo unwinding as a yo-yo traveling down a road that it's creating as it unwinds, because that road is a string. So this portion never moves. The center of mass of the yo-yo moves at speed v, and then, like in that video, I show you that the outer part of this will be moving at speed 2v. And the big thing about the yo-yo is there are portions of the yo-yo, such as the portions that have to do with these parts, the wooden parts, that are moving even faster than 2v. So this could be moving many times bigger than v. The same, incidentally, is true of any wheel that looks like this. For example, a railroad track. If you have a train going on a railroad track, there are portions of the train wheel, because the flanges go below the rails. You can think of this ruler as a rail. So there are portions of the flange that go below it. This shows that if the train is moving at some 60 miles an hour, the top part of the flange, the unflanged portion, is moving at 120, but this portion is moving even faster than 120. So there are portions that are moving even faster than 2v in this case. But other than those kind of interesting remarks, you cannot say anything more about finding the tension. For the tension, you have to go back to Newton's second law. I have to remark that similar statements are true when you have problems, other kinds of problems. For example, if you had an object rolling down a hill, it's the same thing. The object rolls down a hill because of static friction, and the force of static friction can be found in the same manner as we found the force of tension in this example, but you can never find the force of static friction using the energy method, because the point of contact does not move. That's why it's the force of static friction. If the point of contact moved, it would be kinetic friction.